This is the cheapest Nano VNA I could find on Amazon. Let me show you how it works. First, in the case, you're going to find the Nano VNA, SMA, and these are calibration standards, and we need to use these to get the Nano VNA to work. Fortunately, they come in the case. One other thing that was in here is a small little coupler. VNA stands for Vector Network Analyzer. That means this little device can generate a wide range of frequencies and then record a wide range of frequencies and phase. But before you can use it, you have to calibrate it. And that's what these three little devices are for. You've got an open circuit, a short circuit, and then a 50 ohm load circuit. So the first thing I'm going to do is use this little toggle to navigate to the software menu and find the calibration. It might be a little difficult to see, but we've got open, short, load, ISO-LN, don't know what that is, through, done in RAM, and back. So we're going to go ahead and connect the open version of these. So if you look at the connector, you're going to see that there's nothing in it. It's a complete open circuit, but it keeps spare RF from sneaking in. So I'm just going to put that on and get it a little over finger tight and click open. Next up, I need short circuit. Short circuit is going to be the one where there's no dielectric, it's just metal and a metal pin. Okay, that's getting that on and getting it a little over finger tight, and I am going to go ahead and select that. For some reason, load came calibrated. I don't know what that's about, but I'm going to go ahead and put the load on. The load looks like this, looks like a regular SMA connector, and that should be a 50 ohm load. And we're done. As far as through goes, if we were going to use channel 2 here, or I'm sorry, channel 1 versus channel 0, we could connect these with a cable and let them figure that out. This is set up and ready to take measurements. It's a little difficult to see my screen here, so I'm going to go ahead and hook up the Nano VNA to a computer. Nano VNA software is available for free on the internet. Go ahead and download it to your system and then open up the app. We need to make sure that the communication settings are the same on the device as on the computer. So I'm going to go into the settings, into config and connection, and check out the serial speed. In this case, it's set to 38,400. I'm going to go ahead and bump that up to 11,5200 to match the computer settings. The computer, as you can see, is already set for that, so all I have to do is hit connect and wish for the best. So let's go through, just because I've had this thing off and on a couple times, let's go through our calibration setup just one more time. A short connection, a open connection, and then a load connection. And each one of those is going to go on in sequence. Shorts up first. I've got open. I've got load. Since we're at it here, I'm going to go ahead and do a through. And I'm going to make this twice as long as I need to for something that I'm going to do in just a minute. There we go. So we should be able to save that, and then we'll just hope I didn't make any mistakes. The first thing I like to do after I've calibrated is open up the VNA and just make sure that the calibration worked. So one of the ways I can test that quickly is to put on the 50 ohm load. What I expect to see is a flat horizontal line at 50 ohms. And I get that all the way out to about, looks like about 1.3 gigs, maybe 1.4, but after that, this VNA just doesn't know what to do. After that, you're just going to get nonsense. Now, if I do something similar, I put on the short circuit, I would expect this to be at 0, a flat line at 0 ohms. And that's generally what I see out to, a little over the same range. It's actually a little bit further here, but again, 1.3, 1.4 gigs is about the limit of what this little thing can do. Now what we can do with our VNA is take a look at an antenna. This is one that I pulled out of my toolbox. I don't really know what it's for, but it looks like it's a dipole. So I'm just going to take that and hook it up to channel 0, and we're going to hang it here because my workbench is made out of metal, and that will certainly impact the quality of the measurement. Oh, I don't know what I clicked there, but I regret it. So let's go up here, and we should be able to change what it is that we're looking at. S parameters, the standing wave ratio, why not? So if we look at the standing wave ratio, and again, it's not too useful to us to have all of this upper stuff. We might as well go ahead and just stop at about 1.3 gigs. But if we look at the standing wave ratio, if we were trying to operate this at low frequencies, we'd have an absolutely unacceptable standing wave ratio. We could use this at about 191 megahertz. Not ideal. It's a very short peak. You'd have to use it, very close to that. Or we're getting something really nice up here at about 495. Now, I'm going to increase the number of points, see if we can't get a little bit of a better graph showing up here for us. We're still seeing that peak at 191, but the usable range of this is probably somewhere in the 480 to 520 megahertz range. I'm going to go ahead and put this down on my desk now and see if that significantly alters the measurement. I believe that it should do something. Now the antenna's down on the desk and we see a different picture because metal desks are conductors and they certainly impact things. What we're looking at is that we've definitely shifted that far to the left by about 100 megahertz just by having it close to an aluminum workbench. There are a couple other valleys here, or peaks for low impedance, 320, 273, 170 now. Don't know anything about the antenna's performance, but being near metal really affected it. Let's get it away from the metal. Let's get it back into the air here, and let's give it a chance to update. Okay, hanging in a slightly different orientation. Maybe the cable is providing a little backfeed, but we're still seeing that peak show right back up, again in the 500 megahertz range. Now, whether these are true features or not, I really couldn't tell you, but they're there. Let's see what else this thing can graph for us. Let's do a Smith chart on 1.1. Whoa! It's a little ineffective. That's just too much information as it sweeps out all of those. So I'm going to change that from about 400 to about 600, and then we will drill down from there. Run a sweep and see what we get. Okay, it's still quite a bit. What we're aiming for is this little spot right here in the middle for a properly tuned antenna. And we just don't get there. The closest we get is right about here, which is again right around our 500 megahertz range. So at 500 megahertz, where we saw the dip in the SWR, this little guy has an impedance that's actually a little bit over 50, and that's going to lead to some losses. It looks here like it's at about where that peak was at about 500 megahertz. The impedance is about 58 ohms. The real and imaginary parts are a little too small for me to read, but it looks like they're each at about 56.8 ohms. If we wanted to bring this thing back down to 50 ohms, we'd have to add a little bit of inductance to make that happen. All right, I'm going to bump up a little bit of averaging and we'll see what this does. All right, the sweet spot really looks to be about 480 to 520. I don't think we need to waste time looking at the rest of the spectrum for this antenna. So if we wanted to make this antenna, perfect, we would need to get this down to 50 ohms. And the way that you do that is generally with some sort of an inductor and capacitor network. The inductors move the graph in one direction and the capacitors move it in the other. There's a typical type of filter called a pi filter that you can use. The next thing that I would like to do is take a look at this ham filter bank by NooElec. It's got a little micro USB on the side for power, so we'll have to make sure that we give it some power. A bias T voltage, so that means on the antenna side of this, it can put a voltage on, so if you have to run some sort of an LNA or whatever, you can do it through here. And then we've got a variety of frequency bands that this can filter for. So we're going to hook this up to both ports on the VNA and we're going to see what happens. I've got this thing hooked up and ready to go. On the input side, we've got that going to port 0 on the VNA, and the output of this device is going to channel 1, or the second port of the VNA. This is a filter bank. So what this allegedly does is we rotate this around, it should open up some areas in the appropriate frequency range. For example, for 2 meter, we should see something open up on the graph in the 144 to 148 range, probably a little bit beyond that, but let's run a scan and see what happens. In the 144 to 148, are we seeing something? And the answer is absolutely, absolutely. For whatever power that we're putting in from the first port, that's this graph up here on the top, we're getting almost all of it through to the bottom. So that's pretty good. But what happens as we evaluate the rest of these? 1.25 meter band. Let me ask you folks at home, what frequency is that? As we pick these different frequencies, we're going to be able to see how good the bandpass filter is. And all you have to do is just run a scan. At this point, we're set to the 1.25 meter band, and I'll leave it to you to decide what frequencies we should see. Let's run that scan. That doesn't look good. I'm not seeing any strong band peaks anywhere like I would expect to see. I'm going to move it over to through, which should theoretically pass everything. Let's see. So through, no. I mean, it does give a little bit of everything, but there's a ton of loss. We are now set to NA, whatever NA means. Usually it means not applicable, but we'll give this thing a second to run. Interestingly, I mean, there's loss all across the board. What about off? We'll give that a moment to update. Tell you what, let's do single sweeps just to make sure we know when the update's occurring. All right, we are set to off, and right now we're not seeing much in the way of energy passed from one side to the other. We're at 23 centimeters. Do you know what frequency that is? Because I don't, but we'll find out here. All right, so it looks like just up near the end of our useful range, we've got about 1.25 to about 1.3 gigahertz where this is passing the energy really well and rejecting a lot of the energy everywhere else. Remember, every 3 decibels of loss corresponds to a power factor of 2. So 3 decibels, you're passing half as much power. 6 decibels, a quarter. And you keep going on like that, 9 decibels, an eighth. And it keeps going down and down and down. So by the time you get down to 50 decibels of loss, you're not getting a lot of this low energy signal coming through. All right, moving on to 33 centimeters. I'll be honest with you, I didn't even know that was a ham band. Who knew? All right, so we could probably run this scan to clean this up a little bit, but we're over in the 900 megahertz range. So maybe this is an ISM band. Let's see if we can run that again. And it keeps erroring out. It doesn't like that. But you can see that if we ran this repeatedly and increased the number of points, we would see something up here at about 920 megahertz or so. All right, 70 centimeter. Now that's a band I know is a ham band. We're gonna run this, and we can see right up here, we're able to remove almost all the other signal except right up in here, and we're at about 420, 430. So this would be good for the 440 megahertz band. We're going to go to 1.25 now and see what happens. Yeah. See, and I'm just not seeing anything useful happening at 1.25. So I don't know if that means there's something wrong with the switch or if there's something wrong with the filter. But there is nothing coming through the 1.25 meter band. So NooElec, we're going to have to talk. Let's continue. Yeah. All right. So a nice strong peak at about 150 megahertz, what are we at? 144. Okay, so this is the 2 meter band. No problem. We're going to hit through and see if we can pass all the bands. A little bit of energy coming through. Still a ton of loss, but a little bit going through. We're going to hit NA one more time. And it doesn't look all that interesting. And then finally, we're going to hit off and try that. That is 2. Count them, 2 experiments that we did with the Nano VNA. The first was an antenna, and the second was a filter experiment with the NooElec ham filter. And we found that there's something going on at the 1.25 meter range. I'm going to have to do a little more investigation to figure that out, or maybe just contact NooElec and have them send me a new one.